Ana Cavalcanti, so for the keynote. So let me introduce very briefly who she is. So she is a professor at the University of York and holds a Royal Academy of Engineering chair in human technology. And in that role, she is the leader of the Center of Software Engineering for Robotics. And her talk will be based on that as well. So the talk title is Systematic Testing of Drone for PhD unit. So systematic testing opposed to manual ad hoc testing. So I will hand over to Anna for her talk.
Thank you very much. Thanks for the introduction. Thank you. Thank you. Thanks for the introduction. It's a really pleasure to be here and be able to talk to you guys. So thank you very much for the invitation to the premier conference for the early career researchers in the UK. So real pleasure to be here today. And today I have 3 messages for you guys. First message, software is important. And the development of software is an engineering activity. So I am absolutely certain everybody in this room has developed software for their robots. And a bit of programming is not software engineering. Just like any other engineering discipline, you need to use principled approaches if we want to convince people that the very cool robots that we are developing can come out of their cages and be with us. We need to do better with the software. So Rob was talking to us today about his vacuum cleaner, and it may look like, well, the small one that moves very slowly, and perhaps it will bump the cat will complain, not so big. I was going to impress you, well, you could use those vacuum cleaners in a hospital, and then you need to prove that it has 100% coverage. You may use it in a warehouse, and it is very big. It might bump on the stairs and perhaps cause damage to somebody who's up the stairs. But actually, Rob said, even that one has lots of safety concerns. So you might be turning on your vacuum cleaner from home. You don't want it to heat up. So there are lots of safety functions even in that little robot. If we want them to be among us, we can't just look at the software and think, it's a bit of programming. I'll sit down and do some C++ coding. So that's my first message. Software is important, and it is developing software is an engineering activity. Remember that. The second one is about RoboStar. The RoboStar framework, the RoboStar is a center on software engineering for robotics, and it is developing a framework of technologies that allow you to apply principled techniques of software engineering, so that in the end, when you develop your software, you can also provide evidence of its operational reliability, of its safety, and many other things. Okay? So that's the second message, RoboStar can help. And the last message, that even if you're only interested in testing, if you do testing in an ad hoc way, in the end, all you can say is, I haven't found any errors, but they may be there. But there are systematic approaches to testing that allow you to make stronger statements. There will be classes of faults that you can say they're not there. Okay? So 3 messages. Software developing is an engineering technique, endeavor. RoboStar can help, and even testing can provide with more assurance than just say, I cannot find any errors. Okay? So if you are fed up with talks for today, if you were to be had enough, you can now turn off. I won't be upset as long as you promise me you remember these 3 things. Okay? But I will tell you a bit more and try and convince you, if you're not yet, of these 3 points that I'm making. So, what am I going to talk about today? First of all, I'm going to focus on the issue of testing, as Nazmo mentioned. So I'm going to present some motivation for this focus on testing. I'm going to tell you a little bit about the RoboStar framework and the view that we have. I'll present our case study that I'm going to focus on today, which is a firefighting UAV. I'll talk to you about our testing approach, our application to the firefighting UAV of this testing approach, some ongoing experiments, current and future work, and then what more we can do with in the area of testing using the RoboStar technology. So that's what my agenda for today. So testing robotics. Colleagues not from RoboStar. RoboStar is a center with a presence in 6 countries, several institutions. The work that I'm presenting here is developed with colleagues in King's Cross, London, Leeds, Manchester. RoboStar is everywhere, but these were not RoboStar colleagues. They have been conducting surveys with industry, and they have found some interesting things. My whole life, I've been working with mathematics. So every engineering discipline is backed by mathematics. And I've had people saying, I like to write programs. I want to know anything about mathematics. I had never heard anybody say, I don't want to do anything with testing. But in the area of robotics, that happens. So here's what our colleagues found out. Some colleagues in industry say our participants refer to a culture of not believing in the value of testing in their company or institute among not only the roboticists, but also their sponsors and customers. I couldn't believe when I read that. The robotics community are more focused on making cool things than software quality and making things better, even if via testing. Are you guys like that? You're better than that, aren't you? I'm sure you're better than that, otherwise you wouldn't be sitting down in this lecture, I'm sure. So there is another one that's not just one of these surveys. The tester designs and executes tests based on prior knowledge, previous tests, curiosity, and other heuristics for common failures. And that has reported that's been led to people not even agreed whether the test has passed. You have a test and the robot follows a certain trajectory. One expert says, oh, that's good enough. The other one says, oh, not quite right. We need to do better, right? So that's a problem with that. But more than that, manual system testing is expensive and does not scale well. So constrained by the availability of resources, including the time and the effort for setup and execution. So manual testing is the standard approach where people sit and start thinking up, what am I going to test? And then they create by hand lots of tests following we don't know what, okay? So RoboStar vision is that we can do better than that. And I'm going to tell you about the RoboStar vision. And that comes with an invitation there for you guys. RoboStar has been around for 6 or 7 years now, but has now been officially recognized as a center by the University of York. And we have a launch event on the 4th of September happening in York. You would all be very welcome to attend. If you go to the RoboStar page that is indicated there, you will see how you can still get involved. But what's the RoboStar vision? The RoboStar vision is that when you're developing software, where we start with models. You don't start sitting down and say, I'm going to write C++ code for my robot or even for Gazebo. You start by developing models, right? And we have a collection of notations, diagrammatic notations, notations based on controlled natural language that are accessible to roboticists and allow them to write these models. So we have models for software components, for the control software as a whole, models for the physical robot, for scenarios, for operational conditions, for human behavior, and language also to describe the properties of interest, the properties that we need to prove. And today, for the work on testing, I am going to focus on the notations that we have for description of software components and the control software as a whole. But I have here with me other colleagues from the RoboStar team. Holly Henry is there. I will tell you about, if you come to day 3, to the session on the CDT, on lab automation, she'll tell you about what we do in terms of human behavior. Arjun Badial is there as well, and he will tell you about physical modeling. Come to the third day. It's going to be very good. Another colleague is also coming and talking to us about even how we can reason about uncertainty and ethics concerns and so on. So the point of the RoboStar approach is that we have all these possibilities of writing models. Moreover, these models integrate well, and they are all backed by mathematics. They are well-founded, and that enables the development of lots of very advanced engineering techniques, software engineering techniques, that will try and provide that evidence that I mentioned, and that will convince you, if I put my effort into writing these models, then I have some benefits from it. And what they are? You don't need to write the simulation code anymore. You can get the code for the simulation for you. You can get the simulation code, but given the approach that we follow, the simulation code can be used for deployment in the real robot as well. We can generate automatically tests for use in simulation and deployment, and that's what I'm going to tell you more about today. We can even use more advanced techniques called proof that can give you guarantees about the behavior of the robot for every input under certain assumptions. We can use these techniques of proof, model checking and theorem proving, as I said, to provide evidence of properties related to safety, to ethics, and others. We have a tool called RoboTool that's a significant set that allows you to write all these models and validate them and so on. And that is an approach that's application agnostic. Over the years, we have developed several demonstrators. I will, for example, mention this one. It's a dressing robot. It was developed with colleagues in Sheffield, but we have a dressing robot in New York now. This one is an ABB painter robot that was developed by RoboStar Norway. Then there are others. I will today focus on the firefighting UAV, which, as I said, was developed with colleagues in Leeds, Manchester, and King's College London. So this firefighting UAV, it's the result of a collaboration under the program on trustworthy autonomous systems that the UKRI has been running. And the colleagues in Leeds are the mechanical engineers, and they were very excited about new algorithms to use the cameras to detect and locate fires, and the onboard water spraying systems, they developed them themselves. And we have been working on the automation of test generation and execution of these tests as well. What's the idea is that we lower the testing costs because the tests are given to us for free once we have the models. It provides guarantees about absence of faults of given classes, and I will explain to you the way you generate the tests ensures that you are covering a certain class of faults, and therefore, if a system passes all those tests, those faults are not present. Provide support for runtime monitoring. That's the work of colleagues in Manchester. And in this work, we are focusing on ROS implementations. And do we apply our technique in this case study? We haven't finished our evaluation, but so far, we found errors in our own implementation. We have different teams developing and testing. We found errors. And we also found firmware issues that the manufacturer of the robot confirmed and unfortunately didn't fix. But we found them, they were undocumented, and our approach revealed that. So what is our model-based testing approach? When I asked if you guys were as bad as those colleagues in the surveys, you said no. And I imagine that if not, you always start when you're developing your software with some sort of document. This is what I'm talking about here is a document written in English that describes the architecture, the main components of your system, and its requirements. So from that document, you need that. It's just so that the team understands what is being developed. From that document, you will perhaps carry out some hazard analysis, some risk analysis. You will come up with the system properties that you need to check. Right? And these properties may be described in English, but they may be described in a very precise mathematical way as well. You may come up with a test model in a separate piece of work that I'm not presenting today. We have an approach that helps colleagues to create this test model. We start with something very simple, a potential trajectory for your robot, for example, and using testing itself, we elaborate to get to a model of the system as a whole, an abstract model, a high-level model that is specifically for testing. Now working specifically in RoboStar, we use that document as inspiration to specify a RoboChart model. So RoboChart is one of our key notations for description of control software. And in RoboChart, you describe behavior using state machines, more recently using artificial neural networks as well, but I'm focusing on state machines today. Can talk about intelligence at the end if you'd like. And I have put these state machines there in this very dark green. At least it's green on my screen. It is green there as well, perhaps too dark for this screen. But it's to tell you that that's a solid description. You will have seen lots of state machines in papers in the area of robotics. I've seen them. If you've drawn your machine, or if you think the author has drawn the machine using Microsoft Studio or any drawing package, that's not a state machine. That's a drawing of a kind of description of your system. Just like an engineer, a civil engineer make a sketch of a house or a building, that's not a model. They would not put forward the development of their building based on that sketch that's done. They would use a CAD model to actually have something that a tool can read, that you have a clear understanding of everything that it means. That's what I'm talking here. That's what I'm calling him, a state machine in that dark green, right? And colleagues will be developing perhaps some node specifications for a ROS application at the same time, but we end up with this very precise model. From this very precise model, we have techniques that generate specifications of tests for each of the nodes. And so from that RoboChart model, we already developed derived value. From those test specifications, you can get code, test drivers to run with the ROS nodes to check the nodes against certain class of faults. From the system properties, you can get some system monitors, for example, for runtime monitoring. But from the tests, the system properties, the test models, and also this test specifications, you can also get some system-level tests. Tests that you run not for a particular node or collection of nodes, or for the system as a whole. And you can also use those test specifications to inform the development of runtime monitors. And you might think, why do I test? I won't let it go through if it passed the test. Why am I going to be monitoring as well? Well, several reasons. And in the case of ROS, there is a very, very clear one. If you are running your system under testing conditions, you may make sure that it is running with optimal resources, for example. So the communication, the dreaded publish and subscribe of ROS will work well, the message will not be lost, the order will not be inverted, nothing will be duplicated, because in the test conditions, everything is fine. When you go to the runtime monitoring, those assumptions that you made on the test, for example, they may fail. And so you need the runtime monitoring. But it makes no sense to test for one thing and monitor another. So we have that relationship there that we can have with these systems. And of course, someone else is going to be developing the code. But how do we use these tests? One point of the code is that you can use it in simulation, especially in ROS. You can use it in simulation. You can use it for the real system. In fact, the way that RoboStar simulations are developed, it encourages that even if you're not using ROS, that the code that you obtain can be used either for simulation or deployment. But then what do I have here? Well, in testing conditions, I will run the test drivers together with the node code to obtain my test results. And those node codes, they can be used either in the simulation or in the real system with the actual UAV. And the monitors will be associated with the nodes as well. Both the system and the real system and the simulation, they'll provide some logs that allow you to judge whether the test has passed or not, and allows the monitor to understand whether there is a problem or not. So this is the overall idea. I am now going to start telling you a bit more of the details. What's that RoboChart model? It's an architecture and behavioral model. What is it? So I don't really need you to read what's on the right, but it's quite readable, isn't it? But anyway, a RoboChart model, it is a collection of state machines that has a little of a component model, simple component model that groups machines in parallel, communicating synchronously or asynchronously, but it's platform independent. To specify the platform, RoboStar has other models. So the model of the control software is platform independent, and it's based on the notion of capabilities, where you use events and operations as abstractions for the sensors and the actuators of your robot. You can have an event that says obstacle found. It can be a sensor of any nature, a LiDAR, a camera, whatever. You abstract from those the platform details via this notion of capabilities. And if you guys know UML and SysML and so on, you may ask, what's the difference between this and what is already there? Well, there are three differences, at least, or four differences that I will bring to you. First, we have these state machines can specify time budgets and deadlines, so time properties. They can specify probabilistic algorithms. They have a mathematical background that allow us to develop those techniques. And also, they are each state machine is a self-contained component. When I look at state machine in RoboChart, I know exactly what are the operations that it can call, what are the events that it can use, what are the shared variables that it may have access to. So when I'm testing, I'm just saying, I can observe, or I need to observe the occurrence of those events, the operations of the platform being called, and so on. So in my little example here, the battery monitor of the firefighting drone, here's the part that defines the context, and here's a state machine that defines its behavior. I just call your attention, I have two events here representing the input, it's battery info, that's the input for the battery monitor, and battery status is its output. Okay, so tests are about checking the evolution over time of based on this context. So, as I said, observable occurrence of events, values of shared variables, operation calls. And the testing approach that we take is what we call a fault-based testing. So what's the idea of fault-based testing? The idea of fault-based testing is that we think, what can go wrong? And let me try and trick the system to do something wrong. If we can't trick the system to do something wrong, then that means that it's fine for the class of faults that we tested. If we can trick it, then we catch the error. So here's an example, a couple of examples of these test specifications that are fault-based test specifications. They are basically forbidden traces, forbidden sequences of interactions of the component. For my little battery monitor, we can say at the very start, it is forbidden for that battery monitor to output that the battery status is okay, or any other value. The battery monitor cannot give a status if it didn't receive any information. Okay? So that's a forbidden trace. Another one is it received the battery information, and that battery information is saying that it's beyond a certain threshold. BMT is a threshold, doesn't matter what it is. And then it is forbidden for it afterwards to say that it's okay. So these forbidden traces are specifications of tests. Okay? And these tests are, as I said, just tricks that we're going to play with the system on the test or with the node on the test. For example, for the second one, what's going to happen is I will try and trick the system. Here's an input, right? And many things can happen. Of course, it's the battery monitor, we have an eye, but many things can happen. For example, it may not accept that input at all. So it means that I was not able to move the system to carry out this event to follow that very simple trace of one element, right? So my verdict is inconclusive. I wasn't able to check this. Didn't manage to doesn't mean that it's wrong. Maybe the node is doing something else and it's allowed. So according to this fault here, my verdict is inconclusive. But suppose that it does accept that. Then I say, okay, I'll assume that you passed, but I'm going to observe you. I'll keep an eye on you for a certain amount of time. If you then tell me that the battery status is okay, I'll say you failed. And I found the fault, and the fault is exactly that one that's specified in my trace. Okay? So that's how this becomes a specification of faults. But what claims can be made? As I said, it depends on how you generate these tests. If you're systematic, you can say something. And there is no magic. Because of the mathematical background that we have for these notations, we have been able to implement techniques that gives me all the tests of at most a given size. I can say 10 interactions or fewer for my tests. And where would I come up with the number 10? It's not magic. I have to make evidence I have to provide evidence to someone about the quality of my system. So that number 10 will be an expert that knows something about the implementation of the system and will say, if the system has gone, the way it's implemented has gone over 10 interactions, I have already run the system, covered everything that it's doing. There is a strong case, informal case, but a strong case that I have covered all the behaviors and it's fine. So I came up with this number 10. That's the reason why, and that's evidence that I can do. But with that limitation, I cover everything. There may still be too many, and I may need to do some data abstraction, and I can say, my system has a uniform behavior over certain classes of the values of the input domain. Then I therefore do not need to test every one of them. I create classes, and then again I can say to someone who's worried about the quality of the system, look, because of these reasons here, there is this uniformity argument that I'm making, and therefore I have reduced the number of tests I'm making. If I can't do that, I run them all. As long as the domain is finite, I can do it. Another one, which is the one that is, I really like, it's mutation testing. Mutation testing is based on domain expertise on programming, where you say, what are the kinds of errors that programmers will do? And we can then generate all the tests that will catch those errors. I don't want you to think it's magic. It's not magic. How do we do that, right? So I'll try and show you what is the technology that we have to generate these mutation tests. So follow my pointer here. So we start with a RoboChart model. That RoboChart model is given to Robo2, right? We'll develop it with Robo2. Robo2 then provides a mathematical model of that RoboChart diagrammatic description. But that RoboChart model as well is input to another tool called Waldo, developed by colleagues in Spain. That tool, I don't need you to know much about it, but it will know about mistakes that people do in the program, and it generates what we call mutants. Loads of RoboChart models that are very similar to the original one, but they have an error. They have a fault. So we give it to Robo2, and Robo2 gives me the mathematics of it as well. So I then pick up, this is all mathematics, no robot system needed to look at it. It's really beautiful, but you don't want to see it. And then we go give it to FDR, and FDR is going to look at each of them and say, you made that change in the RoboChart model. It had no consequences. It's not a problem, pass. But oops, you introduce an error. Here's what we call the counterexample. That example is a forbidden trace, like I just described to you. So it's not magic. There are tools that can pick up those mathematical theories that we develop and generate those specifications of tests. But what can we do with these specifications of tests? Those are just forbidden traces. You cannot just execute them. So we have developed in Robo2 some extra technology that would allow us to generate C++ code for the tests that takes advantage of ROS infrastructure, Catkin, and ROS test. So here's the RoboChart state machine model. Robo2 can generate a finite number of these test specifications, and we give it to a ROS test generator. The ROS test generator needs a bit more information as well. Remember, my battery info, battery status may be implemented in the node with topics, so with entirely different names, maybe services, other things. So I need a mapping that describes how topics and services map to those events. And then the ROS test generator will generate a whole load of C code for me. So for each test, it gives me a test driver, C++ code that's executable, that uses a library that realizes a mapping between the types that you use in your model and the types that you use in the implementation. They may be different. We can relate one to the other. And each test becomes a Catkin package. We generate ROS launch files as well to use ROS test and execute these tests automatically. There is one bit more that I need to tell you. We, in fact, need to instrument the ROS node a little bit. And I'll explain to you why. First, I just want to explain how to specify this mapping. We created a very simple DSL. It's really very simple. For my battery monitor, we can say, well, here's the test map for the battery monitor. It's for that node of the ROS code, for that state machine of the RoboChart model. I have how the inputs are implemented, so the topic battery state would correspond to the event battery state and so on. I can then say, for that particular mapping, generate a test suite, and then say, use some of those tests. Here we use 303 tests. You could choose some further focusing your experiment. But as I said, the ROS node needs to be instrumented. And why is it? So basically, because there is a bit of a mismatch. And that mismatch is as follows. In RoboChart, it has synchronous communication. I put synchronous there in quotes because it's not like in a synchronous language. If you're thinking of synchronous language like a hardware language, and so that's not what I'm talking about. It's basically that this a high-level model. It's a reactive model. We feel the state machine drawings that you see in robotics papers, they are reactive models in the sense that you have the component in a particular state and something happens, it is interrupted and it changes the state. So it's reactive, it perceives when an input arrives and reacts to it. And that is how the model is developed. That's convenient for us. But in ROS, you don't have that situation. Messages can be lost, delayed, and reordered by the publish, subscribe, and communication infrastructure of ROS. So what we need to do is we need to test the behavior of the model. We need to actually see that the algorithm that's described in RoboChart is properly implemented in the node. For that, we need to observe what the node is doing. If we put a test against the node using just what is published in whatever way it shows up to you, you may see crazy things, think that the implementation is wrong, and it's not implementation, it's just the communication not working quite well. So what we do is that for each input topic, we create an extra topic called input accepted that it's an output topic that communicates the moment where the algorithm actually read the input and is going to use it. And for each service call, we do the same. Service called, service returned, we have timestamps, and it's basically what I call a wrapper. We have a kind of here's my NOS node. I put a lens over it so that I can see what the algorithm is actually doing. Okay? So that's what happened. And then we managed to test the behavior of the node. The test drivers then go in three stages. They wait to establish a connect with the node on all required topics and services. They interact according to the trace, and then they give a verdict, checking the actual sequence of the interactions. They observed all those input accepted and the times and so on. They understand what the trace is, so they check against the ordered trace and give you the verdict. Okay? So that is how it works. So here's an example of what we do. Just to confirm, I have 40 minutes, right? So I still have 31. I saw you moving there.
Yeah, you 7 minutes, 7 more minutes.
7 more minutes. Oh, right, okay. I think you stole me a minute, but it's fine. I will give you that. Okay, so the test drivers. So here's the example that I gave you. It's slightly different. That one that says battery state, given input 0, and then mission critical is forbidden. So what do? We generate some code that drives the node in the test and then wait for a given amount of time. Initially, it gets those messages, the instrumented ones, and then says, okay, I assume that it's inconclusive for now, but I now try to observe battery state in with the value 0. If I observe, I say pass. If I observe that afterwards the mission critical and out, then I say forbid. And this is the part of the code that we generate. And with simple cat-kin and ROS test commands, we can then provide a report for our system. So our case study. The RoboChart model of our case study is rather large. We have two things that I wanted to tell you about it. The robotic platform of a RoboStar model describes those capabilities that I mentioned. They are abstractions of the sensor and the actuators. And our colleagues in Leeds said, well, the embedded API is fine. We are not worried about the embedded API, we are worried about our work. So they basically trusted the embedded API of the DJI. So we have operations that are, and events correspond to calling and return the raw service of the DJI. We have operations for the actions of the pump and the gimbal, and that is how we start writing our model. What are the things that we trust? If we don't trust, we model, we develop code. If we trust, we say that's a capability that we use. Okay? So that's the first important thing. Then we have two controllers corresponding to the two processes, and each controller has several machines. That's a large model. In the case study so far, we have done some node testing with tests in C++ and Python, running on a virtual machine. For the battery monitor, we have done 303 tests that generated some issues because of hard-coded timeout in ROS launch that led us to improve our technology. For the watt monitor, two, that's an interesting example as well, 2 of the tests failed. And basically, because the water monitor was allowing you to, it was actually ROS that was messing things up. It was allowing you to receive a command to turn on or turn off the pump when actually you shouldn't do that at the beginning. And then we noticed that, actually it doesn't matter. It's receiving that input saying that the pump is on, the pump is off. It doesn't matter. It is the model that was too restrictive. In the context of the system, the model was too restrictive. So that's another possibility that we can have as well. So our evaluation is ongoing, and we have 2 research questions. How effective is our approach in preventing faults? How complementary are the different verification techniques in detecting the different faults? And our experiment to answer those 2 research questions is done using mutation, but now mutation of the C code. We got the code that our colleagues in Leeds developed, and using an automated process, we developed a whole load of faulty implementations to check if our tests were good, if our tests would pick up an error that had been genuinely made by a programmer. So we had tests of components and systems, and we computed the metrics. The metrics is basically how many of the faulty pieces of code that we generated are actually found out, killed the mutant, found out by our tests. So one important thing is that we automated that mutation because we could make an error ourselves in creating a mutation. 17 out of the 50 mutants were useless. That's because of the way the tool that we developed worked. One thing that we noticed is, for instance, if you mutate our instrumentation, that's not useful for us because our technique assumes that the instrumentation has been done properly. So using our tests, we eliminated them as well. And then we saw that there are several kinds of faults in these mutants that we can catch. Communication errors, duplicating messages, missing message, functionality, making the wrong calculations, providing the wrong output, temporal, delaying messages too much, and so on and so forth. So this is ongoing work. Because of time, and I want to tell you a few other things, I will talk perhaps just about the battery monitor, but we've done 3 of the components. All the mutants were killed, and we're quite happy that 11 by component tests and 14 by system tests. So showing a certain complementarity, right? Just the components test is not enough, just the system test is not enough. We need to run them both and have that kind of complementarity. So in summary, for this part of the talk, and I will take my 3 minutes to tell you a couple of other things. We have a comprehensive, highly automated approach to testing, combines extension and adaptation of existing techniques and tools. And this combination, this automation is enabled by the mathematical foundations that allow us to have this seamless integration in the workflow. In the future, we'll be thinking about, can we avoid the instrumentation by creating a testing API? And then we don't touch the code at all. But we can automate that instrumentation as well. This is something that we're going to talk about. event-based communication, ROS2 tests, time tests. There is lots of work to do, but it's so promising what I've seen. It's so exciting and so on. So 2 things I wanted to tell you. We have approached, this is what we've been doing for us, but we have also been working with RoboStar Germany, which is a company called Verified Systems International, who has a prized industrial tool that works for UML and SysML. And that's a tool that's being used in the automotive and the avionics domain. And they want to expand into the robotics domain. So they are working with us with their qualified multi-platform tool to allow us to roboticists to use their work as well. And what's really pleasing is that the approach is as follows. We have a RoboChart model. Another model of the RoboStar family is the RoboSim model that describes a simulation. It's not reactive anymore. It's a cyclic mechanism. And using exactly the same technique, the same test case specifications, we can develop test procedures that are to be run against simulation code that is generated from RoboSim, and then we can use that as input for an entirely different tool. Because our starting point is models, is specification, and develop these techniques, they're very general. Doesn't matter. RT test can be we want to use our report. We can also use ROS, as I just explained to you. Another thing that we need to be careful is if you're using a simulation, then if you are now comparing a reactive model with a cyclic model, we'll need to have to do some conversion. I don't have time to tell you much more about this. There is something else that I want to tell you. The environment is also key. The environment is key because here's an example of a drone. We applied the technique to this case study and got this test here, which according to the software specification is correct. The drone takes off, one time unit passes, it receives a call to move, and it's to move towards the target to find a fire or a person or whatever. But the test says, well, now assume that I found the person or the fire or whatever, immediately. If you look just at the software model, you can get a test like that. And basically what's happening is that the software does not know that it makes no sense for us to think that the drone will take off, start moving, and then found the fire right where it started. That doesn't make sense at all. So RoboStar has another notation called RoboWorld that just allows you to write some assumptions, environment assumptions. So we have assumptions about the arena, about the robot, other elements. So we can say, we're using this language that it's English, isn't it? But it's mathematics. There is mathematics behind it. We can say the arena has a target region. Initially, the robot is at the origin. The distance from the target to the origin is greater than 1 meter. With this, in the mathematics that's behind it, we are able to devise an algorithm that just says, and please, ooh, what happened? Oops. I don't know what happened here. I'll have, just give me 1 minute. I have to go all the way down there. Oh, really unfortunate. I'm not sure what happened there. But I just have one more little bit to tell you. So we're using the mathematics that comes from RoboWorld. We are able to then say, and this test, discard, it's not useful. Okay? So that is what we are allowed to do. Conclusions, takeaway message, RoboStar model framework. Software is important and it can help you. It can make it easier for you to test your systems. It can make it easier for you to construct simulations. Collection of domain-specific notation of techniques that provides, and these techniques for model transformation, simulation, and test generation was our focus today. Reactive model-based testing with adaptation for ROS and cyclic mechanisms, including considering the environment via RoboWorld. Future work is further automation, reasoning with these RoboWorld models. It's very exciting because they are now bringing quite complex and hybrid, what we call hybrid model, and lots more experiments. So I always finish my presentations like this. RoboStar is an open community. If you found that interesting, if you'd like to work, to apply the RoboStar technology, be in touch. We'd love to collaborate and work with you. We're very welcome to RoboStar as well. Thank you very much for your attention. Thank you.
I like your enthusiasm. Enthusiasm for software.
Yes.
Yes, so any question? Yes. So let's try this one. Okay. Can you catch?
Okay, thank you very much for the presentation. Can you hear me now?
I can hear you.
Okay, so I'm from University of York as well, was Eureka Abundance Scholar back in 2010, worked with Jim Woodcock.
He's one of the founders of RoboStar. He's going to be here tomorrow.
Yes.
Or tonight, actually.
Yeah, so I worked on the perfect developer. You were talking about the ROS and the testing in ROS itself as well. One of our project is working in ROS 2. So we are, from last 3 years, working in ROS 2, worked in the sim-to-real thing in ROS 2 itself as well, and worked on a lot of robots. But of course, testing is important. And because my research, how it initiated was in the verification and validation of the software, right from the requirements, and then I still believe heavily in that. So I was thinking that as AI is now becoming the enabler in the robot, can we, and you understand the question what I'm going to ask, can we use this to enable it, whether it's in ROS 2, because a lot of our models are going into, and you were hinting on one of those, like Bayesian, sort of Bayesian thing, that we are getting expert opinion to understand that 10 number is coming from the expert itself. It's not a magic. So can we use that over there? That's first question. And then I have a second question regarding, you have worked on the DJI Tello drones, which I understand. Is it portable on the other platforms as well, on the other machines, interfaces, robots or industrial robots kind of thing as well?
Thank you very much for your questions. First of all, we should be working together. But yeah, first one about artificial intelligence techniques that are so important today. We have just recently the extended RoboChart to allow you that the controllers that are originally can be only specified using a collection of state machines. They can now be specified by the hyperparameters of a trained network. If you do that, if you're talking about a trained network, the clue is in the name. It's a network. The sort of mathematical models that we use, they are very suitable to capturing that, the meaning of what that network means. It has fitted really, really well. The challenge that we have is, you saw that I talked about comparing, for example, comparing mutants to the system. We need tools that can cope with those models. Neural networks will make the models very large. So what we are working now is, instead of using that kind of technology that's called model checking, you know what I'm talking about, we're using theorem proving and give you a symbolic description of the tests. So that's something that we're working now, using a theorem prover called Isabel, so that we can use exactly the same approach. As long as you have the model, and we can now do it, you can get the tests. All right? So that is possible to do. That was the first question. The second question you asked me is, does this work for other ones? Yes, because the model is platform independent. I really thank you for this question, because it allows me to explain. The issue of capabilities is extremely important. When you make the software platform independent, it means when I'm bringing it to actually test against a real system, what I need to do is to understand how those services are implemented in the real system. That's how we get the fact that we can move from one to the other. So RoboStar Denmark was just, they started working with us. They were just absolutely amazed because they were not using ROS, they used different technology, and for the first time they experienced a situation where they wrote a simulation, they work with digital twins and therefore developed simulations, and because of the way we've done, they were able to pick up the simulation code and put it in the real system. All they needed to know is, well, the simulator provides those services in one way, the actual robot provides the services in a different way. So I trusted those services, so there they are, unplug one, plug the other, and nothing changed in your software. The same thing, the tests, you would have exactly the same interface. Platform independence is extremely powerful if you do it properly, okay?
Any further question?
Thank you for the presentation. I apologise if this is the same as Samal's first question, but you mentioned that the model is reactive, so essentially it picks up on certain bad behaviours and stops it. I wonder if you could make it proactive, so they guides behaviours, kind of a line in terms of artificial intelligence.
That's not quite what I mean by reactive. What I mean by, I think perhaps an interrupt-based is more accurate thing to say. So what it means is that when the robot is in a particular state, it's not polling anything. It doesn't have that cyclic behavior of a simulation, right? A simulation has an idealized paradigm. Read all the inputs, do the processing, provide outputs, wait until the next cycle and go again. A cyclic executive is like that. A reactive model is not based on polling. I'm there in my state, an input arrives, I note, I change my state. That's what a reactive model means.
Could you make it proactive?
Proactive in the way that you are describing would not be about the paradigm of the model, but it would be about what the functionality is that you want to model. Yes, we can. We can describe proactive, what you're calling proactive, but it is not, your proactive is not the opposite of my reactive, let's say.
Right.
Let's say like that. But we can do it. Yes, we can do it.
Any further question? Rob?
Yes, can you apply this, can you apply kind of compliance and safety rules to this as well? So if I've got a safety control function, how does that fit into your model?
Okay. Safety control function. What we have one other case study where we are working with this. That's with RoboStar France.
Yeah.
They have developed a piece of hardware, a safety platform, which is certified and is to be dedicated to carry out the safety functions of a drone. So in particular, for this kind of example, it is going to be doing a bit of the battery monitor, and basically it's going to be polling the communication base, and if it doesn't hear, then decide there is a problem, I don't want to lose my drone, it needs to land. And so what we are doing is the safety function is specified by a state machine.
Yeah.
And then when we specify it as a state machine, we can apply it in the same way. One thing is their technique is cyclic based. It's not reactive. So instead of using RoboChart, we're using RoboSim. But then it works. And the reason why it works is, remember at the beginning when I put my picture, there are all the models and they connect nicely, all with mathematics. It's because the same mathematical theory that's behind RoboChart is behind RoboSim. So this summer, an undergraduate student came and implemented to us the test generator for RoboSim. We had it for RoboChart, he did it for RoboSim. It's as, undergraduate students in New York are amazing. But they're not experienced roboticists, and they were able to do it over the summer. That's because it's the same. It's the mathematics behind it that is driving that generality, let's say.
Yes, yeah, great. It'd be really interesting to see if you could take the RoboStar framework and then take it to a compliance or safety test house and then present the information to get compliance or safety.
My colleague Arjun Badial tomorrow is giving a presentation where he will talk about work that he's done with the Center for Safe Autonomy, and that will talk about safety cases. So he may address some of the things that you are talking about. He's agreeing with me there. It's work that he's done independently from me. It's work with this other group. He won a competition because he used RoboSim, of course, and so he'll tell you about that.
Okay.
Okay?
Great. Yeah, thank you very
Great.
much.
Thank you very much.
Thank you all very much. Thank you.